screen. Okay. And meanwhile, please prepare to have your iClicker. So for today's lecture, we will still have a little bit iClicker question. So as you can see from the screen, today we are going to talk about epidemiology. So I guess most of you probably have no idea what is epidemiology about, but I'm pretty sure you know like what is epidemic because right now we are exactly in the middle of the pandemic era. So in fact, epidemiology is closely related to the infectious disease. So you know, like in according to WHO, there will be three different categories when we define the level of the infectious disease. So at the lowest level will be so-called the endemic. So for the endemic disease, it will be mostly like the disease will happen case by case, and mostly those cases won't related to each other. But for epidemic, which is probably the case of the COVID in the early of this year in China, it is called epidemic, where we do see a rapidly growing infected individuals around a certain region. But the good thing is that the epidemic is just contained in a certain specific region. However, if we are the disease is crossed all over the world, then we will call it pandemic, and that is the worst scenario we will expect. Because in that case, all of the countries in the world will be involved in this pandemic situation, and almost the cases could be connected to far enough away. So although the epidemiology, this word is coming from the word epidemic, but actually we also discuss the statistic in also in other two scenario in the endemic and the pandemic situation. So to discuss the epidemiology, it will be very interesting to know like how statistician will react to the rapidly changed situations. So what statistician will do is basically play with math, right? So in this case, they will specifically trying to find certain important measures to describe like how serious our situation is. So so imagine if you want to describe how serious the COVID-19 is, what kind of measure you would firstly look at? I guess the at least the first thing come up to my mind is like what's the percentage of the individual get disease of the COVID-19. So this is exactly the definition for the most important measure, which is the prevalence. So the prevalence is referring to what's the proportion in our population that those individuals get disease. So basically, if you imagine this orange individual as the infected person, and the blue individual, the health person, then our prevalence is basically given by the count of the infected individual divided by the entire population, which is contain both the health individuals as well as the infected individuals. But as you can imagine, for the prevalence, it's important to talk about at what specific point we are looking at, because our epidemic situation or pandemic situation is changing very rapidly. So in that case, it's important to distinguish the two different kinds of the prevalence. So the first one is called the point prevalence, and another one is the period prevalence. So the difference is located in at what time point we are looking at. So for the point prevalence, specifically, we're only looking at a certain specific time. And so it's pretty much you taking a snapshot. And after you taking a snapshot and you just count, okay, at this time, how many individuals get disease and how many don't. And for the period prevalence, on the other hand, it's like you record a video. Say if you record the video for a whole year, and then you just look during this year, how many individuals are sick and how many individuals are in a health situation. So I guess for now, you probably still have no idea like what's the specific difference of these two prevalence. So let's try an exercise. So this is a very simple toy example where we only have 100 individuals in our population. And let's say only 10 of them have ever diagnosed with the disease in a whole year. And the remaining 90 individuals, they are all healthy and they are all alive for the whole year. So to easily present like at what specific time those individuals get diagnosed, we displayed their situation of the diagnosis using this timeline plot. So basically, if you look at these plots, so each row will represent the situation for one subject or one individual. So for the first individual, we can look at that the line is from the first day, the January 1st, till the last day. So basically that means this individual is get disease for the whole year. And for the second individual, we use a crossover sign to denote that this individual died at May 1st. And for the third individual, although he was sick for the first 8 months, and finally he was cured at the September 1st. And we use the triangle to denote that at what specific time the individual was diagnosed with the disease. So basically, we're ignoring the remaining 9 individuals because they are all healthy and alive for the whole year. So we didn't need to record their information over there. So now let's do some exercise then. So first of all, we have learned about the point prevalence and as well as the period prevalence. So then first, let's figure out what's the point prevalence of the on the July 2nd. So based on our definition so far. So basically our definition of the prevalence is that you can consider it as the proportion of the diseased individual in our general population. So in our case, what's the point prevalence at the specific time point? So for this type of question, because for point prevalence, we are talking about some specific time, right? So here, we're only looking at the July 2nd. So if you draw a line over here to represent the July 2nd, it's pretty much like this, right? And I get some result. Yeah, it's pretty, yeah, that's very good. So, so if you look at our definition, we first look at how many individuals get disease. So you just count like how many individuals were diseased at this specific time point. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 individuals get infected. So our numerator will be 8. And the denominator, remember, the denominator is the population at our specific time point. So the tricky part for this point is that we have to exclude these 2 individuals because these 2 individuals already died at July 2nd. So in fact, our denominator should be 98 instead of 100. So this is the tricky point when we calculate the point prevalence. But for the period prevalence, it's actually much easier because for the period prevalence, we just look at what's the prevalence in the whole year. So if you look at how many individuals, it's just 10, right? Because we only have 10 individuals get disease in this whole year, and the denominator will be 100 because there are in total 100 ever appeared in our time interval. So the period prevalence in this case will be very straightforward. It's basically 10 over 100. So far we talk about prevalence, but some people might wondering like, I don't care about how many individual get disease, but I want to know like how quickly people get infected. So in this case, we are kind of look at dynamic situation. So in that case, instead of just look at the prevalence, we will look at the so-called incidence. So for the incidence, it's kind of looking at the change over two time points. So for the prevalence, we are looking at the fixed time, but the incidence, we are looking at the difference of two times. So say from the time one to the times two, we have two individuals get infected over this time. And in this case, our incidence will be defined as the number of the new individuals divided by the total individuals in our population. So which means the formulation will be just our diseased person divided by the all of the person, including the healthy individuals and the sick individual, and also the new diagnosed individuals. So again, come back to our example, if you look at what's the cumulative incidence for the whole year, we basically just do the same thing. First of all, we count how many new cases. So we have 1, 2, 3, 4, 5, right? So that's why our numerator is exactly 5 in our cases. And also, remember the denominator is including the entire population. So because our entire population is still 100, so our cumulative incidence will be 5 over 100. So very interestingly, there's a very approximate relationship between the prevalence and the incidence. So we say the prevalence is approximately equals to the incidence multiplied by the disease duration. So here we use the approximate relationship because we're not saying that we can use this relationship to exactly calculate our prevalence just according to the other information. But what we can learn from this relationship is that we can have a good sense of what is the change, or what is the level of the prevalence according to the two other, or we can infer the situation of the incidence according to the other the levels of the other two measures. So for example, if say we have a small incidence and a small disease duration, and in that case, definitely we will know that our prevalence will be very small. So a nice example for this type of scenario would be rabies, right? Because for rabies, it's a really rare, especially in the developed countries like Canada. And also the disease duration is quite small because the disease is developed very quickly and people could die very soon. So that's why you can imagine, like in our general population, there's not so many people get diagnosed with this type of disease in a whole year. And if you look at another situation, like we have a small incidence and large disease duration, and in this case, our prevalence will be definitely larger than our previous case. But still, because the incidence is so small, our prevalence could be very low. So for this type of situation, the one example that comes up on my mind is the HIV, the virus. So for this disease, because once an individual is get this virus, and they will carry this virus for the entire life. So which means the disease the disease duration is really large. But on the other hand, we didn't see like there's so many individuals like in a large proportion in our population, right? So that's kind of can help us to infer that the incidence of the HIV is actually very, very small. And if we look at this situation, say we have a large incidence, very large incidence, and a very small disease duration. And in this case, we could have a little bit higher prevalence in our general population. Does anyone have any idea about what type of disease could happen in this situation? Let me put on the chat.
Maybe like a cold or like,
Yeah, that's
yeah.
exactly what I uh, that's exactly what I thought. So, because like for codes, the incidence is extremely high because for some individual they could catch the cold multiple times during the year, right? But on the other hand, the disease duration is quite short because usually it takes just 7 days or 1 week to get recovered, unless there are some other disease accompanied with the cold. And as for the last type, oh, the mentioned Ebola. Yeah, I'm actually not quite not sure about Ebola. I believe the incidence of the Ebola is not very large in a sense. I think it actually depends on the region we're talking about. Um, because example for rabies, like I would say for Canada, the incidence of the rabies is extremely small. But for some other developing countries, the rabies could this disease could be really have a really high incidence. So every time we talk about the prevalence or incidence, we have to be specific at what countries we are talking about or what region we are talking about. And for the last example, the large and large, actually, it spent me a really, really long time to think about the example for both the incidence and the disease duration, um, uh, for both of the to be high. So, anyone has any idea about what disease could have these type of features? Actually, it takes me really long because I just because in that case that means our prevalence will be extremely high, right? Because both our incidence and disease duration could be very high. So finally, I come up with an example which is nearsighted, because maybe this is also related to the region we're talking about. Maybe in Canada it's not so bad, but I would say at least from my experience in China, the prevalence of the nearsighted is very, very high. I would say approximately 60% um, around that point. So, uh, as you can imagine, in that case, once you get nearsighted like me, and you will always be nearsighted in your entire life, and also we can actually infer back about the incidence just according to the prevalence and the disease duration that definitely the incidence itself will be really large. So if you look at uh, our if you summarize our relationship of incidence or prevalence into this graph, I actually really like this character. So you can consider our prevalence is like a pool. So it's basically telling us what's the uh, at some specific time point or specific time period, how many individuals get disease. But the incidence is more like a dynamic situation. So we want to look at what's the change in the infected individuals. So far, we only talk about these two, and we miss a very important information. And this information will also reflect how serious a disease could be, which is the mortality. So mortality, or sometimes we just call it the death rate. So sometimes we just care about how deadly our disease could be, or how many individuals could die from a certain specific disease. So in that case, we will look at like what's the level of the disease will cause the death. So we actually have two different measurements according to our objective. So say if we want to say, okay, for a general individual, how likely for this uh, individual will die from certain specific disease. And in this case, we will look at the mortality rate. So mortality rate is basically defined as the number of the deaths of a certain disease divided by the total number of the individuals in the population. You can imagine that the margin, sorry, the mortality rate is a kind of like the prevalence of the death. So it's defined in a similar idea, but mortality rate is just talking about death, and the prevalence is talking about disease. And sometimes we just more we care more about like how fatal a disease is. Like if one individual is diagnosed with the disease, then we want to know like what's the percentage or possibility that this individual could alive or survive from this disease. And in this case, we will not look at the mortality rate because mortality rate is for a general population. And in this case, we will define the fatality rate. So fatality rate is just looking at the a particular disease for individuals with disease specifically. So actually, for this case, our numerator is the same as the mortality rate, but the denominator will be different because our denominator will only focus on the individuals in our population who already got the disease. So mostly like for COVID, I guess right now we care more about the fatality rate because we don't consider the COVID-19 as a certain like a coincidence thing, like a car accident or like a air crash. So for that case, we more talk about mortality because that's more like a coincidence. But for COVID, it's not like that case. So we care more about fatality rate, and specifically, we want to know like how good is our our health resources in our country. So we want to know like if we have a large amount of our large group of individuals get disease, and we want to know like how many of them could survive. So in that case, we usually talk about fatality rate. So far, according to my experience for COVID-19 in Canada, our fatality rate was very high in the early periods, especially in the April or May, and it's gradually get down because we have the reason for our fatality rate get down is mostly because we have more individual get diagnosed. Because at the early stage of the COVID-19, our calculation of the fatality rate could be problematic because our we don't have that many test kits. So in that case, a lot of individuals, although they actually diseased, but they won't be tested. So we missed a lot of individuals to be test positive in our population. So that's why at the early stage, our fatality rate is extremely high because that's not because we did so bad, but it's just because we missed a lot of individuals in our denominator. So that's the case for a pandemic situation in general. So back to our example, say if we want to calculate the mortality rate and fatality rate, so we just follow the definitions in our formula. So basically, for the mortality rate, we look at like how many people died in our general population, right? So in our case, we have 1, 2, 3, 4, right? We have 4 individuals died, and in total we have 100. So in that case, our mortality rate is just so simple. It's for over 100. And sometimes we would like to times 100 percentage to make it into a percentage because percentage is always easier to understand. And for fatality rate, based on our definition, because we only have 10 individuals get disease and 4 all of them died, so the fatality rate is actually really high. It's almost 40%, which is it's actually really I would say it's already a very deadly disease for this example. Okay, any oh, I have some questions. Okay, let me see. Chicken pox. Oh yeah, actually I have no idea like what's the incidence of the chicken pox. I understand. I agree that the disease duration could be really long. But of course, when we talk about the length of the disease it's usually more a relative idea. It's usually comparing with the other type of the disease. And uh, and some students mentioned allergies. Yeah, I agree that allergy has a really high incidence. Oh, yes, that's a very good point. Actually, I do have allergy too. So I agree that this allergy could be a good example for this case. Because uh, for some for some cases, I'm not sure whether the disease duration could be high though. Because for some cases, the allergy could be take really long, even for years, right? So I mean, for uh, if you imagine for a general population, there's still a lot of proportion of individuals who have allergies. So I think that's a good idea. That's a good point. Yeah. Any other questions for the the epidemiology part so far? So I guess uh, for this part, we basically just talk about several very basic idea or concepts in statistics. But of course, there's still a lot of things to do. Like there's a lot of question. For example, recently in Western Ontario, uh, there's a research group in department working on in the prediction of uh, what's the individuals what's the amount of the individual who get diseased after the next year, and also some research group will measure like what's the influence of the vaccines that helps to reduce the infections. So for this area, it's actually a very open area and involves a lot of research. And I guess the COVID, because we are in the middle of the COVID pandemic period, so I guess the good thing is that we have a lot of cases to study that uh, what's the situation of the disease, and it we have a lot of data to validate whether our statistic model is correct or wrong. But still, we hopefully we can propose uh, our models to help the government to find the best measure to the general population so that we can finally get over the disease. But I guess the best way is still to wait for the vaccine because that's the final or the best practice to finally get over this pandemic situation. Okay, any other questions? Okay, if there's no other question, I'm going to head into the second part of today's lecture. So, so for this part, I actually let me see if I can. Okay, I actually prepared music because I would like to conclude the first by bringing back to our starting point. So in the first lecture, we talk about statistical thinking, right? And in these 12 lectures, and you have almost 24 hours in total to listen to me talking. And okay, wait a second. I'm not sure whether that can you hear me? Okay. Okay. Never mind. Then I'll just turn it on. Oh, I stopped sharing. Okay. Yeah. So in these 12 lectures, you have spent like 24 hours in total to listen to me talking, and even longer time to put all of your effort in the course. So I would really appreciate that. And Maybe at the beginning you were afraid, dislike, or even hate the topic of statistics. But I hope that you will find the examples that we discuss in the course to be interesting and helpful. And more importantly, I hope that you can regard these 12 lectures as a journey to acquire a new way of thinking, which is what we talk about the statistical thinking. So maybe before you care a lot about whether a thing will happen or not, but now you also care about what the chance of the thing happen. And maybe before you thought that we can easily draw a causal relationship, but now you understand that a lot of relationships, they are just correlation and they are not causal at all. And maybe you won't work in the statistical fields in the future, but at least when you read an article in our social media or certain media, you won't rationally believe their conclusion. And instead, you will also looking at their assumptions and the study design. So basically, all of the statistic problems can be categorized into four problems. The first one is the visualization. So in lecture 2 and 3, we talk about the two different ways to describe our data to our general readers. And we also focus on how to avoid the misleading interpretation of our results. So this is actually very important because nowadays we have a huge amount of the data, and it's very important to make sure that you can properly present your ideas in using the graphs or in using the measures. And we actually spend almost half of our course to talk about the second problem, which is the inference, where by inference, we mean that we look at the specific sample, and we hope that we can just based on the data of the samples to infer or guess what the general population looks like. And we talk about two different inference problem and two different aspects of the inference. For example, we talk about the correlation problem and also the estimation problem. And we also compared the confidence interval and also the hypothesis testing. And all of this problem actually can be summarized into an inference problem. And unfortunately for this course, we don't have chance to talk about the classification. So basically classification is to trying to use the data to summarize our object. And then based on those characteristics, we're trying to categorize them into different subcategories. And for the last topic is called the prediction. So we actually talk a little bit about prediction. So for the prediction, we use the example of the Cheeto, where we use the regression to predict what's the heart rate given a certain walking distance. But in fact, for prediction, there could be a lot more work to do, and there's a lot more sophisticated situation to predict, like how to predict the pandemic situation in the future. That's still a very interesting problem. And another thing I would like to say that although statistic has been applied in many, many fields and many, many areas, and despite that, we still cannot say statistic is all powerful or is perfect because there's still a lot of problems that statistics cannot do. So here's an example. Sorry. So here's an example. So say we are trying to predict what's the stock price in the future, because like based on our historical data, we can predict whether it will go up, go down, or remain the same, right? So in this case, we can use this model to earn money, right? That sounds very fancy. But a very interesting fact is that almost all statistical models will fail after once. So why is that? Why that happens? Because some models they are actually really good for some period of time at the beginning, but ultimately these models will fail anyway. So that's a very interesting research area. So in fact, there's a lot of reason for why statistics not working so good in this example. So first of all, when we talk about statistics, we do make a lot of assumptions. For example, in the previous lecture, we talked about we assume the normality or approximate normality issue, but sometimes that is not true. And also, for a lot of study, they just assume that there's no confounders. But as you can imagine, there could be a lot of other factors could be our confounder issue. And also, like sometimes we just assume there's no sampling bias. For example, in our election polling, we assume there's no sampling biases, but in fact, that's not true. And another problem for the statistic is that uh, that failed in the stock price is that the stock price is actually a chaotic system. What it means is that every time when we do prediction itself, it will actually influence our prediction in the general future. So that's why our prediction so far is it probably works sometimes, but it will generally fail in a certain period. So in this case, we need to combine our statistical knowledge with the other disciplines, such as economics, sociology, and psychology, etc. So the take-home message for this piece is that even if in the future you are not going to work in the field of the statistics, but I hope that you can still try to combine your knowledge with the statistics. And in that way, you can still contribute to the statistic area. And finally, I would like to share with you some of my personal stories. And some of these stories actually uh, entirely changed my personality. So basically, I have spent like 10 years studying statistics. And I would say definitely by applying the statistical thinking, it, it changed a lot of personality of me. So the first thing I would like to share is that, like a long times before, I was really a intense individual, and like I always strive for excellence or strive for perfect, and I hope everything is under my will control. And every time when I realize there is something that out of my control, I will feel extremely panic, and I kind of break down. And sometimes I work really hard, but in that case, I start to very worried about whether my results could pay off my hard work. And that gives me a lot of pressure and I get very panicked. And sometimes I didn't even get a very good result because of that. So while I studied statistics, I gradually realized that actually randomness is everywhere, and we need to admit the existence of the randomness in our real life. So remember in the lecture 6, we talk about the measurement, right? And we say that our measurement or observation is equals to our true value plus the randomness. So you can kind of consider these true values as our real level of the understanding of certain things or our true level of our effort. So so in that case, even if you tried so hard to have a large true value, but you still can have more or less results because of the randomness. So what I want to share is that in that case, I hope that you can just focus on the true value itself. So all the effort that we're trying to put and all of the time we spend is just to improve the true value itself. But we have to admit, okay, there is a randomness, but we don't need to worry about that because randomness is just not the thing we can control. So my suggestion or my what I want to try to say is to just to focus on the true value and improve the true value of yourself and forget about the randomness and don't care about it. And my second thing that I learned from statistics is actually learn from the confidence interval. So as I said, I used to be a very intense person. Like I always chase for 100% sure. Like every time when I make mistakes or make an error, I feel extremely bad. And sometimes I feel so sad for a really long time. And this type of mood or sentiment sometimes give me a lot of negative power. So I feel really bad during that times. But after learning the statistic, the confidence intervals inspired me a lot. So if you imagine your life as finding a confidence interval, so if you want to chase for 100% sure, then in that case, you have to create a confidence interval for infinitely long, right? And in that case, you can get 100% sure. But as you can imagine, to create a 100 or infinitely long confidence interval, that takes a lot of time, effort, and it might be not necessary. So sometimes it's important to allow for the existence of the error or allow for a certain margin of the error, because when you have a larger margin of the error, you have a wider confidence interval, and then you will have a higher confidence level. And more importantly, we should always try more and practice more. And in that case, we will get a much more sample size of ourselves. We will get more knowledge of ourselves. And finally, as a reward, we will also get a much higher confidence level. So basically, what I'm trying to say is that the most important word in the confidence interval is the confidence itself. And sometimes we just need to allow for some margin of the error. And in that case, we will allow for more possibilities. So I, I hope these words can come up to it with the music, because that sharing will make more sense. So these are just my very personal thoughts, and that's like that's my thoughts. That's not what I got at a certain point, but I gradually kind of understand from when I exposed to the statistics. And maybe you don't buy it, but I hoped that you can learn more. You can always learn more beyond the knowledge itself. Because sometimes knowledge is not just knowledge, but it's more like a philosophy. So finally, if you happen to get very interested in the statistics, and you want to learn more in an advanced level, then here are several courses you can go for in the following semester. So say if you want to learn more in mathematics, like in this course, we kind of skipped a lot of the mathematics derivation. But if you want to know that, so there's a probability and statistic one that you can start with. And also in this course, I didn't require you to learn like a statistical computing, but like it's nowadays it's very important to at least to know some coding language. So I think it's quite useful to learn some like a programming, especially for this statistical programming. So maybe in the future you could considering the courses like the statistical computing. And finally, I want to thank my TA. So they helped me a lot for this semester, because I'm a new instructor, and they gave me a lot of suggestions and helped me a lot. And they are also great people to work with. And finally, I would like to thank you, because you are my first batch of the students, and I also learned a lot from you guys, and I wish you all a success in all your future career or studies. Thank you. Okay, so this will conclude all of the courses, and let's have a 10 minutes break. And so if you don't have any other question, you feel free to go, but I will stay here for the Q&A session to answer the questions. Okay, thank you guys. And it's really nice to have you guys be my students. Thank you. Okay, so let's have 10 minutes break. Um, then we will get back at 2:25. Thank you, guys.